Hello everyone, we are going to go over the Unit 2 practice free response questions that are very similar to the one that will be on the summative on Friday. So for question 1, we always start by reading the actual question, so let's do that. It says, for A, predict the protein powder's main function. So of the protein powder, emphasis on the protein here because this is biology. We just talked about macromolecules last unit, so it probably has something focused on the protein. And identify its monomer, so the monomer of the protein. So this one, we don't need any background information that we read. We have to know what is the function of a protein and what is the monomer of that protein. So, proteins, as we know from our macromolecule project, have a lot of different functions that include things like enzymes that speed up reactions, that break down food, that do a lot of different things. For this one, because we're talking about how it changes mass, and we know that that has to do with like water transport from the osmosis lab. The protein that we're probably talking about is some sort of transport protein that's in the cell membrane. And so I'm going to answer this like this. The protein powder's main function is to transport molecules across the cell membrane. The monomer is an amino acid. Again, you just need to know that from background knowledge. We talked about this first unit. If you don't know, you should study this. Wink, wink, nudge, nudge. Look at this for carbs. For carbs, the monomer is a monosaccharide. Okay, so you are going to need to know this for the test on Friday. Now, let's look at B. It says, using the most appropriate data, so we're going to be choosing from here what would be the most appropriate data, construct a labeled graph on the axes provided below to best illustrate the water movement into and out of the protein shake. Explain why there is a difference in the percent change in mass of the protein shake in the different protein powder solutions. So I need to make sure I talk about all of the different solutions. That's why I boxed this, because that's how many. All right. So let's just start with constructing the labeled graph. Now I'm going to actually go back and read the background information. And it says, a student conducted an experiment to determine the molar concentration of solutes in a protein shake, or in protein shakes. The protein shakes were placed in protein powder solutions of different concentrations. The data are shown in the table below. And so we have the protein powder concentration. This, because we're determining if the molar concentration affects the change in mass, this is going to be what we control. So this is going to be our independent variable. And we know that independent variables go on the x-axis. So I'm just going to go ahead and write that on my x-axis. Protein powder concentration. And because it has units here, I'm including units here. Anytime you're giving a table, just write exactly what you find in that table on the axes and for the title. And so that's our IV. And then I'm looking at it here. We have the initial mass and final mass. So remember, that's what we measured. And then we had to do some calculations to figure out what we graphed. So then we found the change in mass. And then we converted that into the percent change in mass to see how much actually changed within each solution. So this is going to be your dependent variable, and it goes on the y-axis. So here, I'm going to write percent change in mass. And for our title is always dV versus IV, but we don't write that here. We write what our dV is and what our IV is. So we have percent change in mass versus protein powder concentration. And again, include the units if they're provided in molar. So now let's actually graph it. First thing we need to do is find our scale. Find our scales for both the y-axis and the x-axis. So for the x-axis, our highest number is 1. And then I'm going to go through and count how many lines there are. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. There's 20. So every single line is going to go up by 1/20th. But because this data is only 0, 0.5, and 1, instead of going up by every 1, over here at the very end, I'm going to label this 1. And halfway through, so 10 lines through, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, I'm going to label this 0.5 molar. Okay, because that's just halfway through. And then here is going to be your 0 molar. Now it's a little trickier for the y-axis. We go here, we see that our largest number in either direction is negative 23.6. It's not 15.6 because this number, even though it's more negative, is larger. So we're going to choose this one to be our lowest. We're going to round to about negative 24. Come back here, count down how many lines there are. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Take that 24, that negative 24, divide by 10 to figure out our scale. When we do that, we get negative 2.4. That is going to be very difficult to count by, so we are going to round up to 3. So here we're going to go down each line by 3 and up each line by 3 because it needs to be an even scale on the entire y-axis. So here, 3, 6, 9, 12, 15, 18, 21, 24, 27, and 30. I'm going to go down the same amount, but I'm going to make it negative because it's below 0. So negative 3, negative 6, negative 9, negative 12, negative 15, negative 18, negative 21, negative 24, negative 27, and negative 30. Okay, so now that we have our scale, this is the easy part. We just plot our points, knowing that this is going to be a scatter plot. And it's a scatter plot because we are seeing the relationship and the trend between this concentration of the protein powder and the percent change in mass. So at 0 molar, we have 15.6 being our percent change in mass. That's approximately here. So I'm going to make my dot. For 0.5, it's negative 11.8, very close to negative 12, but above it. So I'm going to make my dot there. And for 1, it's negative 23.6, again above negative 24, but still really close. Because we don't have error bars here, we don't need to include error bars. If we did, we would take these numbers and add your 2 times the standard error and subtract 2 times the standard error. That gives you the top bar and the bottom bar. But again, we're not doing this because we're not given 2 times the standard error. All right, let's go ahead and move on to part C. Oh, see what I almost did there? I almost missed this question. So this is a big thing with the graphing questions. Usually there's going to be some explanation based on the graph. So always go back and check B to make sure you're answering the questions. So again, it says, explain why there is a difference in the percent change in mass of the protein shake in the different protein powder solutions. I'm going to go back here. And this one has sentence stems and hints that are very helpful. These will not be given on the test, so you need to know what I'm looking for, which is why I gave you this now. So my hint is, talk about what happens when a protein shake is placed in different types of solutions. So in hyper, hypo, and isotonic. And go from there. Now, this one, we don't have any solutions that are isotonic, because if we did, it would be directly on the x-axis where your percent change in mass is 0. So this one we're just going to talk about hyper and hypo. So here it says protein shakes gain mass if placed in a hypotonic solution because water moves into or out of the cell. Well, if it's gaining mass, it's moving into the cell, and it always goes towards solute. So here, they gain mass in the hypotonic because the water is moving towards the solute, and there's more solute inside of the cell than outside, because outside is hypotonic, and there's low amounts of them. Now we have protein shakes lose mass if placed in a hypertonic solution. Again, so it's opposite here. Maybe there's like 1-ish solute inside and a whole bunch outside. That's a hypertonic solution because water moves out of the cell, again towards the solute. Okay. So again, water follows solute. If it's hypertonic inside the cell, it's going to go towards there. If it's hypotonic inside the cell, it'll move out. If it were isotonic, our drawing would look like this, where maybe there's 2 solutes in, 2 solutes out, and water is going to move in and out equally. It doesn't just stop. Again, molecules are always moving, but it moves in and out equally. So now that is B. We are officially done. Let's move on to C. It says using the data, so I probably have to look at the data table. Determine the molar concentration of protein shakes and justify your answer, knowing that this is 3 points. It will also be 3 points on the exam on Friday. So here it says you can use the table or graph and you can give a range of molar concentrations that could include the correct one. Don't forget units. So if I'm looking for the molar concentration of the protein shakes, that is going to be where my percent change in mass is 0. So it's somewhere between 0 and 0.5 molar. So that's where it changes from positive to negative. So here, the molar concentration of the protein shake is between, 0 and 0.5 molars. When the percent change in mass is 0%, this means the water is moving into and out of the cell at equal rates. So instead of into the cell or out of the cell, it's both into and out of the cell at equal rates. This means the solution is isotonic, and the solute concentration inside the protein shake and outside of it are the same. So this is like the drawing where, say that's my protein shake, it's put into a solution, we have 3 solutes inside, there's 3 outside, and it's moving in and out equally. That is what I'm looking for in the test on Friday when you're talking about 0% change in mass and linking it to how water is moving. D, we are going to predict how the addition of more membrane proteins would affect the rate of diffusion of protein powder into and outside of the cell. And we're going to justify the answer. So this is basically saying, here's my phospholipid bilayer. Now I'm adding more membrane proteins that span across this phospholipid bilayer, which allows the protein powder to move more quickly. Okay, right? It would increase the rate of diffusion if I'm adding stuff in here that allows it to move more quickly. So here's my sentence stems. The rate of diffusion would increase. Proteins require what for passive transport? Proteins require protein channels. Protein channels for passive transport, meaning they can only do facilitated transport. Now this sentence feels weird because you're saying that proteins require more proteins. There are, like I said, a bunch of different proteins that do a bunch of different functions. And so these proteins are always going to be large, and a lot of them are going to be polar. And so they need some protein channel in the cell membrane to help them move across. And that means it's facilitated transport. Simple diffusion is when they can go straight across the phospholipid bilayer. Facilitated transport means you need some sort of protein channel in the phospholipid bilayer for it to get across. And then it says more proteins in the cell membrane means more area for the solutes to cross the membrane. Right? If I'm putting a bunch of these proteins in, then we're going to have more ability for these proteins to get across. All right, last but certainly not least, we are going to calculate the osmotic potential, which is also known as the solute potential of a 1.2 molar sucrose solution at 32 degrees Celsius. So this one, you do need the AP equation sheet, and we have to label what is given. So this says it's a sucrose solution. A sucrose solution is always 1.0 for I because it does not ionize. C is given that it's 1.2 molar. R is always going to be 0.0831 liter bar per mole Kelvin because that is given on the formula sheet. And then T is going to be 32 degrees Celsius plus 273 to make it Kelvin. Oh man, I can do math. This is 50. So this is 305 Kelvin. 305 Kelvin. So now we just plug it into the solute potential equation. Again, that's the one that looks like that. So it's going to be negative ICRT multiplying each one. So solute potential equals -1, which is just negative. You almost treat that as if it's not there, because 1 times anything is itself. Concentration is 1.2 molar. R is 0.0831 liter bar per mole Kelvin times 305 Kelvin. So let's just make sure all of our units cancel out except bars. Molar is moles per liter. So that cancels out with liter per mole. And then that's times Kelvin, that's divided by Kelvin, so those cancel out. So then we are left with, let me do the math, negative, and if I'm doing this here, negative 1 times 1.2 times 0.0831 times 305. We get negative 30.4. Negative 30.4 bars, because that is the only thing left that is a unit. So this is your answer to E. All right, good luck studying.